Hi class, this is Sir Alex again and welcome to our lesson in General Chemistry 2. And this is the start of our second quarter of our lesson in General Chemistry 2. And today we'll be talking about Lesson 7.1, and this is the rate of reaction. Okay, so the end of the lesson, our goals would be for us to be able to understand how reactions actually proceed and the rate by which they occur. Moreover, for us to be able to describe some various factors that actually influence the rate of reaction. Okay, so before we begin discussing about the rate of reaction, basically when we say rate of reaction, it's how fast a reaction happens. And that is influenced with our understanding of chemical kinetics. Let's first ask the question, how do reactions proceed? For most of you, you may think that it simply proceed by adding two atoms together. For example, water or H2O is just an addition of hydrogen and oxygen. So if I take an atom of oxygen and an atom of hydrogen and put them together, voila, I can make water. But that is actually not reactions work. Reactions work in essence like a demolition derby. I'm not sure if you guys are familiar with demolition derby, but they're just basically a bunch of cars in a field similar to this, and their goal is to bump onto the other people's car until only one person is left standing with a moving car, and then they win. Kind of very similar with bumper cars. If you guys have been to Enchanted Kingdom or Star City and have experienced riding bumper cars in your younger years, you may have experienced like random people bumping into your car or you bumping into someone else's car. And in essence, a reaction is actually very similar into this process. So, for example, you have H2O. You want to create H2O. You need atoms of oxygen and hydrogen. What would you do is you present those two atoms together, those atoms of oxygen and atoms of hydrogen, in an environment, and you want to let them to start bumping into each other. Sample this one. This should be moving. Um, Let me just. Okay, there you go. Okay, so it's as you can see, it's moving right there. So what happens is you introduce oxygen in atom, and we know that molecules move, and as they move, they bump into each other, and if they bump hard enough, and they bump in a proper orientation of bumping, that's when products are formed. That's when chemical reactions happen. So, for example, here you have atoms of hydrogen and oxygen. So the oxygen are initially together. If you guys are if you seen, probably did not see it, but at the beginning of this moving picture, the two circles or the oxygen are together because O2 are usually together the same way oxygens are. And as they bump into each other, the oxygens break up the same way that the oxygens break up and the hydrogens break up, and then they form into new molecule, two combination of molecules, two atoms hydrogen and one oxygen, creating water, and that happens through bumping of those ramming of those hydrogens and oxygen. So the chemical reaction is basically just a bunch of chemicals ramming into each other. And when they hit each other hard enough and they hit at the right orientation, a product is formed. And this study of collision between chemicals and the movement of the chemicals that affects the rate of reaction is a study of chemical kinetics. Now let's go to rate of reaction. So the rate of reaction is basically how fast the products form. So we are measuring how fast products form or how fast the reactants are consumed. Rate of reaction is basically a measurement of the change in molar concentration of a reactant or a product per change in time. Because rate, when we talk about rate, this is basically over a period of time. And what we are measuring over this period of time is actually the change in the concentration of reactant or product. So rate is basically equal to the change of concentration. And in chemistry, when we talk about concentration, we usually add brackets on the elements. So for example, if you want to talk about the concentration of, let me just use my pen here. So for example, you want to talk about the concentration of hydrogen, you use brackets, or the concentration of, let's say, NaCl, sodium chloride, molar concentration, or basically concentration, we use brackets. So when we measure rate, we are measuring a change in concentration over a change in time. And the units that we use is molar over or molar per seconds. So for an hypothetical chemical equation, A, sorry, this should be A. For a hypothetical chemical equation, A plus BB, and then proceeds to CC plus DD, A, B, and C. The small letter A's, small letters are the coefficients in your chemical equation. And the capital letters are your elements or your atoms or your molecules. So for example, we have this hypothetical chemical equation. To measure the rate, this is the equation that we actually have to use. Rate is equals to 1 over the coefficient of your first molecule or atom. And as you can see, we have negative signs. Negative signs are usually reserved for the reactants. And the reason for that is because as chemical equation or as chemical reaction occurs, the reactants lessens while the products increases. That's why for products we have positives. And what we do is the rate is equals to the negative 1 over the coefficient of the change in the molar concentration of your first element over the change in time. And that is actually equal also to the 1 over the coefficient or however moles or coefficient of the second molecules or elements you have multiplied by the change in its what we call this change in its molar concentration over time, etc., etc. The most important thing here is remember that if you're dealing with reactants, you have to add negative. So an example, we have here a chemical equation. Two atoms of N2O5 in gas form decomposes into four atoms of NO2 in gas plus 2 plus oxygen. So it's a rate equation for this chemical equation. We have to follow this. So again, this is our reactant and this is our product. So the rate would be equal to 1 negative 1 over 2. That's the coefficient. This is your big letter A, and then the change in the molar concentration of N2O5 divided by however time the change in time happens. It can be 2 seconds, 1 seconds, depending. And equals to, again, this is positive because now it's product. 4 is the coefficient of NO2, so that's 1 over 4 multiplied by the change in the molar concentration of NO2 divided by delta change in time. And that's also equals to, as you can see, it doesn't have any 1 over because the coefficient of the oxygen in our chemical equation is 1. 1 over 1 is 1. So it's basically equal to the molar concentration of oxygen divided by time. So having said that, or having understood that, I hope you guys that's clear. Let's try this problem.